So what was the problem with the Rutherford model? Yeah. What was the issue with Rutherford's model?
It's having, the science hasn't. Call it caught up to him.
But what was it about the classical physics that posed a problem to Rutherford model? Well, this isn't a bad test question for you kids.
Yes.
What are your classical physics accelerating charge of gravity and energy? And you guys know from physics that velocity is a vector quantity. So if you speed up the field enough or change direction, the thing gets up, right? So if we imagine an electron in the nucleus, if it's orbiting in the nucleus, it's constantly changing direction, right? Therefore, it's an accelerating charge. According to classical physics, that electron lost any energy. It would spiral into the nucleus instantly. It should lose energy because it's a charge that's changing direction. But there was a firm mathematical and experimental evidence for that to happen. A serious challenge to Rutherford's atomic model arose almost instantly. A very secure prediction of the physics available at the end of the 1800s was that accelerating charges should radiate energy. If an electron radiates any energy, it slows down. If it slows down, it collapses into the nucleus. That prediction was catastrophic for Rutherford's model. It meant that all atoms, and therefore all matter, should collapse. The Rutherford model, in other words, had no way of sustaining it, at least according to the physics available to humankind at the end of the 1800s. Obviously, a significant piece of the atomic puzzle was missing, and even Rutherford himself was ready to abandon his view of the atom. Rutherford was a physicist. He knew full well that accelerating charges should radiate energy. We can demonstrate that. Alternating current in a wire. Alternating current, which is what we get out of the wall here, the electrons change direction 60 times a second. They're accelerating. That produces radio waves. So it wasn't a theory. It had been shown that accelerating charges radiate energy. The real problem, though, was not the model. The model was fine. The real problem was that the physics of the day needed to be rewritten, not just modified, but rewritten to explain the behavior of electrons and atoms. That's the only problem. That's the problem at the end of 5.1, which we're going to solve today. That's the problem at the end of 5.2, which we're going to solve in 5.3. The nuclear model was fine. The neutrons and protons, no issues. It was the electrons that weren't behaving the way they should. To begin to understand how the solution came about, we must consider the work of German physicist Max Planck, literally at the turn of the 20th century. In 1900, this conservative professor began nothing short of a revolution in physics. He proposed that energy, long considered to be strictly a wave phenomenon. A wave phenomenon is a continuous function. Look at a rainbow. It's raining and the sun's behind you, you see a rainbow. All those colors wash into each other. Red gradually turns to orange, to yellow, to green, to blue, to indigo, violet. All of the energies in the visible spectrum play out as a continuous spectrum of color. Energy in the form of electromagnetic waves is exactly that. We mentioned last class that what's the job of a wave? It moves energy. But energy, considered a wave phenomenon, is what scientists refer to as a continuous function. So, for example, the amount of water in this flask, I can change by any amount. I can change it by a little or a lot. That's a continuous function. The amount of water I can add to the beaker, any amount I want. I can change the amount by any amount. That's a continuous function. This isn't. Each of these marbles is wood. If I wanted to add or remove wood from this beaker, I could only do it in whole number amounts. That amount of wood, one of those, two of them, three of them, four of them. That's not a continuum function. Only some amounts and not others. The people in this room. That's a particle property. Hopefully there's no fraction of people. I can add or remove people from this room in the form of whole numbers. That's a quantum phenomenon. What Planck was suggesting based on his research, and if you want to Google his research, Google black body radiation. What he found based on studying the energy radiated from heated solids. The energy he was putting into these solids was continuous, but the energy coming out wasn't. There was some amounts and not others. Planck's experiments showed that under some circumstances, energy long considered to be simply a wave phenomenon was behaving like particles in the form of very tiny, discrete packets or bundles of energy. He called quanta, plural for quantum, like the wood marbles in the speaker. Planck called this the quantum theory. Quantum means particleized. And he arrived at his conclusions, albeit reluctantly, by studying the energy radiated from heated solids. Planck developed the following equation for the energy associated with one of these packets, a quantum of energy. The amount of energy was equal to a very tiny constant times the frequency. Now, in physics, you probably use a little f for frequency. That's sort of this is a Greek letter mu. It's kind of a v that's been squashed. So that's that frequency. H was called Planck's constant. Now, you don't have to remember this number. All you have to remember is it's really tiny. Okay, that's the important part about H. It's really tiny. So obviously, if this is really tiny, then the energy of one of these packets is really tiny. But the point is, energy could not be divided into fractions of these. Energy could only exist in one of those, two of those, or three of them. In other words, energy was a quantum phenomenon, particle. One quantum, two quanta, three quanta, four quanta, but nowhere in between, no fractional amount. Think of energy quanta of an energy quantum as a glass marble in a bag of identical marbles. In the same way that you could only ever add or remove a specific amount of glass from the bag in the form of a whole number of marbles, so too could amounts of energy only be absorbed or emitted in the form of whole numbers of quanta. At the end of the 1800s, the behavior of waves and the behavior of particles were seen as very different and mutually exclusive. This is kind of what the warm-up was intended to suggest. Waves were disturbances that moved through space, could pass through and interfere with each other, and could have any value within a range. That's the continuous function. Particles, though, were objects with definite boundaries that bounced off each other when they collided, but only exist in certain whole numbers. A firm experimental and mathematical foundation supported the idea that waves and particles were fundamentally different, mutually exclusive. To now suggest that waves could behave like particles was almost sacrilegious. Planck was a tenured conservative professor with a reputation, but he proved himself to be a pure scientist by writing this: "By nature, I am peacefully inclined and reject all doubtful adventures." In other words, he doesn't go down meaningless rabbit holes. However, a theoretical interpretation had to be found at any cost. I was ready to sacrifice every one of my previous convictions about physical laws, if it meant explaining the data that he was gathering. And that means he's a pure scientist. He's not concerned about his reputation. He's concerned about gathering knowledge. Planck's theory wasn't taken very seriously at first, as is often the case in science. The scientists are trained skeptics. They don't believe stuff because they're told. That's the whole point of science. But when they do sit up and take notice, when they do see what amounts to effectively a revolutionary idea, when they start paying attention to it, is when it does one or two things. If it explains something that was previously unexplainable, and or if it predicts something correctly years down the road. The quantum theory, to be accepted, had to do something for scientists. It had to solve a problem, it had to make a prediction. Well, the first problem that it solved was a mystery that had baffled physicists way back in the 1800s, called the photoelectric effect. 5 years after the quantum theory was proposed, a 26-year-old clerk in the Swiss patent office who had just completed his PhD but was struggling to find work, took work in a patent office to support his wife and his young child. In 1905, he wrote several papers that changed the scientific world forever. One of them you probably at least have heard the result of, E equals mc squared. Another was special relativity. Another was Brownian motion. But the one he got the Nobel Prize for was his explanation of the photoelectric effect. As the name suggests, this has something to do with light and electrons. Now, we're not going to go into it in too much detail, other than just showing that the only way to interpret or to explain the photoelectric effect is to see light as behaving as particles. So, what is the photoelectric effect? So let's say we have the surface of a metal, and we cause on that surface of metal incident light to be contact. So electromagnetic radiation, usually in the form of light, hence the photo part, is shone on a metal surface. As the frequency of the light goes up, and if frequency goes up, so does energy. At some point, we reach what is called the threshold frequency, the minimum energy, which results in electrons being emitted from the surface. And these are often referred to as photoelectrons, because the light causes them to be emitted from the surface. So once we're at that threshold frequency, the photoelectric effect is what comes after. As we increase the frequency, the energy of the incident light, we don't knock off more electrons. In other words, the number of electrons emitted has nothing to do with the frequency of the light. As the energy of the light increases, all that happens is the energy of the electrons emitted increases. But the number of electrons doesn't. In other words, we can't knock more electrons off as we increase the energy of the incident. The only thing that happens is the energy of the emitted electrons increases. The only way to increase the number of electrons emitted from the surface beyond the threshold frequency is to increase the intensity of the brightness. So, simple example, let's say red light is the minimum. It's not this simple, but let's say as infrared won't do. As soon as we hit red light, we get an electron. If we go from red light to green light to blue light to violet light, the same number of electrons come up. They just come up with greater energy. The only way to make more electrons come up is make the red light brighter. In other words, the intensity of the light. And if you want to use a wave analogy, that's the wave amplitude. Amplitude is intensity. So the only way to get more electrons to come in is to increase the intensity of it. Increasing the frequency does not change the number of them. The number of electrons is a function of the intensity. The energy of electrons is only a function of the energy of the light coming in. Now, how does seeing light as a particle explain it? Well, let's imagine that this is maybe the edge of a counter or a tabletop. And let's say that on the edge of that countertop, I've got some bowling pins. Line them up. You're lined up on the edge of that countertop. And I want to knock them off. And I'm going to knock them off by maybe lobbing a cork at them. So here's my cork. So I lob the cork, hits one of the pins kind of does this. Pick the cork up, throw it a little harder. Doesn't happen again. Pick the cork up, and finally I throw the cork hard enough that one of these pins gets knocked off. Okay. Now I pick up the cork, put the pin back up here, and then I throw that cork even harder. Am I going to knock more pins off if I throw it harder? I'm going to knock the same pin off. It's just that the pin's coming off with more energy, right? What's the only way to knock more pins off? More corks. So this is the packet of energy. And it was later called photons by Gilbert Lewis of Lewis structure. The only way to explain the photoelectric effect, that the number of electrons is only a function of the intensity of it, is to assume that light is little particles. The only way to get more electrons off is to throw more photons. But you can't get more electrons off by energizing a photon. Just like you can't get more pins off by throwing a cork harder. You're just going to knock the pin off harder. You're not going to knock more pins off. Now, if light was a wave, that wouldn't be the case. Increasing the intensity of the wave, the brightness is the only way to get more quarks, more electrons. But increasing the energy of the wave, if it was just a wave, should have the same effect. We should knock more electrons off if the energy of the wave increases. But that's not the case. Now, why is this matter? And why did Einstein get the Nobel Prize for that in 1921? Well, one of the big reasons is that the scientific community began to say, maybe Planck's theory is actually correct. Maybe energy does behave like particle. Okay? Why does that matter? Well, one of the scientists who paid particular attention to the work of Planck and Einstein was a young Danish physicist named Niels Bohr. By paying attention, he means, okay, there's probably something to the quantum theory. Maybe energy really can be some values and not others. Maybe energy really is quantized. As a young grad student, Bohr had met Ernest Rutherford at the Cavendish Laboratory in Cambridge, working with Thomson. And he also worked with Rutherford at the University of Manchester, where the nuclear model was proposed. Bohr believed in the nuclear atomic method, and he started to see a way to save it using the quantum theory. In other words, that energy was particleized. If energy was indeed quantized, and so could be seen to have only some values and not others, perhaps the energy associated with electrons orbiting the nucleus has similar restrictions. Bohr was working on this idea at Rutherford's lab in Manchester in 1912. That's about a year after Rutherford proposed the nuclear model. In the middle of his experiments and calculations, he returned to Copenhagen to get married. He was so excited about his work that he managed to convince his new bride to cancel their honeymoon, well, postpone it, and return to England with them. Soon after, Bohr completed one of the most brilliant papers on atomic structure ever written. Now, you're going to see two videos in this chapter. One of them is kind of a PBS video. Another one is a little more scientific. But in the first one, it mentions that when Bohr lived at home, when he was working on his master's and stuff, the video said he seemed to have a serious phobia about writing. So he dictated all his scientific papers to his mom. And that upset his dad. Bohr did not have a phobia of writing. He had dyslexia. So it wasn't that he didn't want to write. It's that he put this. They didn't know what dyslexia was back in the early 1900s. When he got married, he dictated this paper to his new bride, and you think that for a woman. Well, Bohr got very rich and very famous very quickly, so it was okay. But it wasn't that he had a phobia of writing at all. It was dyslexic. In the previous section, we discussed the conduction of charges through gases in glass discharge tube. Remember, that's how the electron was discovered. The scientists were investigating these things for years. One of the things that energy being released from gases in discharge tubes had shown science was another mystery that was previously unexplainable. So Bohr knew that when high voltage was applied across the electrons of a sealed glass tube containing a gas such as hydrogen, the gas was heated and emitted light. Scientists knew that. You look at a rainbow. Let's say you're in a rainstorm and stuff behind you. You see, as I said, a continuous fall, right? All the colors wash into each other. The low energy end of the visible spectrum is red. The high energy end is violet. But you see all the colors in that continuous spectrum. If the light by an energized gas in that's having high voltage run through it, if you look at that light though with a prism, it's a spectroscope is basically a prism fitted with an eyepiece. If you look at that light, you don't see a continuous spectrum. Bohr looked at this light through a spectroscope. Spectroscope is a device similar to a prism which separates light into its component wavelength. But if you look at the light released by energized gases, what you see is a series of colored lines against a black background, not a continuous spectrum. We see only some colors and not others. Some wavelengths and not others. Some energies and not others. You can't really see it too well here, and of course the book isn't in color. But this is what you see whenever you look at the light released from hydrogen from a gas discharge tube. Without the spectroscope, it looks kind of like a pale violet. But when you look at it through the spectroscope, you see 4 lines. You see a red line, that's the wavelength, 656 nanometers. But you don't see anything here. You don't see a nice wash of orange and yellow. Then you see a blue-green line at 486. Notice as the wavelength goes down, the energy goes up. Then nothing in here. Then you see a blue line, higher energy, 133.9 nanometers. And then you see a violet line. But you don't see anything in the each color corresponds to a specific wavelength, specific frequency, and a specific energy. So what was coming out of these glass discharge tubes was discontinuous, only some energies and not others. The phenomenon had mystified scientists. For hydrogen, the same pattern of 4 colored lines was always seen. But for every gaseous element used, a bright line spectrum unique to that element always appeared, kind of like the barcode in a grocery item, but not a continuous spectrum, ever. The phenomenon had mystified scientists. None could explain why only certain colors of light, each corresponding to a specific wavelength, frequency, and energy, were emitted by the heated gas until Bohr. So Einstein used the photoelectric effect, used the quantum theory to explain the photoelectric effect. That gave credence to the quantum theory. Then Bohr said, okay, if energy really is quantized, maybe I can use that to explain this. And by explaining this, he also saved Rutherford's mind. Bohr realized that by applying quantum principles to the behavior of hydrogen's lone electron, He could not only account for the existence of the bright line spectrum, but also save Rutherford's nuclear model of the atom. So here's how he did it. According to Bohr, based on the bright line spectrum of hydrogen. The hydrogen atom had only certain allowed energy levels, or we call them stationary states. Each of these states really corresponded to a circular electron orbit of a fixed size. The larger the allowed orbit, the further the electron from the nucleus, the greater the energy. The larger the allowed orbits, the greater the energy associated with it. Thus, the further the negative charge would be from the positive charge in the nucleus. No other orbits existed in the atom, only certain sized orbits and not others. Each allowed energy state, each orbit of a specific size, was given an integer number n that Bohr called a quantum number, with allowed values ranging from 1 to infinity. Now, why to infinity? Because if we keep giving the electron energy, at some point, we ionize the atom. But Bohr said these are the sizes of the allowed orbits. N could equal 1, 2, 3, but nowhere in between. The lowest energy corresponded to the smallest orbit. And that would be the orbit when an atom wasn't absorbing energy. And Bohr called that the ground state, kind of like ground level. Anything else, he called an excited state. So as long as an atom was existing in a state without being energized, like a high voltage current running through it, as far as hydrogen is concerned, that electron would be in that lowest allowed orbit. So let's say that's the nucleus. Hydrogen's ground state, or ground stationary state, let's say would be F. That was N equals 1. Bohr calculated the energy of that orbit, and that corresponded to a specific radius. It was even called the Bohr radius. And according to Bohr, when a hydrogen atom wasn't absorbing energy, that electron would be in that circular orbit, a specific distance from the nucleus 100% of the time. How did that explain the bright line spectrum? As long as the electron moved in an allowed orbit or stationary state, the electron and therefore the atom didn't radiate or absorb energy. The only way an electron absorbed or radiated energy is if it, in terms of absorption, if it absorbed an energy specific to the energy of the next orbit. So if this electron is going to absorb energy, say from high voltage in a glass discharge tube, unless it gets that amount of energy, it's going nowhere. It can't exist anywhere in between here. So if it's going to go up to the next allowed orbit, it has to absorb a specific amount of energy. The only way it's going to radiate energy is if it moves from one allowed orbit of higher energy to another. So it had to absorb a specific amount of electron to get to the next orbit, and it would therefore emit that same amount of energy if it went from a higher to a lower. Anything higher than the ground state, Bohr called an excited state. And that would require the atom to absorb energy. But once an electron was in an excited state, it didn't stay there. It would come back down. But in coming back down, it would emit a specific amount of energy corresponding to the difference between a higher orbit and a lower orbit. Just like being on a staircase. I get here, or I can be here, I could be on the next step or the next step, but I can't be anywhere in between. And unless I have enough energy to go up to the next step, I stay put. If I come down a step, my decrease in energy is exactly equal to the difference in height between the higher and the lower step. If an electron absorbed enough energy to go up to the third, or the fourth, or the fifth, or the sixth, it was always a specific amount of energy. So let's call that the third allowed orbit, fourth, 6. How does that explain the bright line spectrum? Let's continue. The electron could only move from one allowed orbit to another, up or down, if it absorbed or emitted an amount of energy exactly equal to the energy difference between the two orbits, delta E. This meant that the hydrogen atom could only change from one stationary energy state to the other. Let's take a closer look. Postulate 1 employed Planck's theory by quantizing the energies associated with the electrons in a hydrogen. Only certain sized orbits were allowed. In other words, that energy was fixed. Couldn't be anywhere in between. Think of the electron as a ball in a staircase. Just as the ball can only rest on any particular stair and so have only certain amounts of potential energy and not others, so too is the electron restricted to only specific energies and not others. Postulate 2 meant that the nuclear model of the atom proposed by Rutherford would not collapse. Because according to Bohr, if an electron was in one of these allowed orbits, it didn't radiate energy. And the obvious question would be why? Bohr didn't know. He didn't know why the energy levels existed. He didn't know why if an electron was in one, it didn't radiate energy. He just knew it had to be that way to explain the bright line spectrum phenomenon. Let's talk about the bright line. Bohr calculated the distance between 1 and 2, that energy difference. If an electron got enough energy to go up to 2 and was in that excited state, when it came down, it would release that specific amount of energy. Bohr calculated that that energy was too great for us to see. That's in the ultraviolet region. Anything down to 1 was in the UV region. So 2 down to 1, let's say an electron got enough energy to go up to 3 and came down to 1, too much energy for us to see. 4 down to 1, 5 down to 1, 6 down to 1. We couldn't see any of those because they're in the ultraviolet region. Bohr predicted they'd be there, but we just couldn't see them. But if something went up to 3, an electron went up to 3, and instead of coming down to 1, came down to 2, that energy is what we can't see. That's the red line. So that energy, that wavelength, corresponds to the lowest energy form of visible light you can see, red. 4 down to 2 corresponds to blue-green light. Higher in energy, lower frequency. 5 down to 2, that's the blue. 6 down to 2, that's the violet. Now, notice that the energies get closer together as we go up. If we wrote in 7 here, 7 is really close to 6. 7 down to 2 looks violet because there's not enough difference there. But those are the only 4 lines we ever see. What about something down to 3? Well, something down to 3, like 4 down to 3, 5 down to 3, 6 down to 3. That's energy too small for us to see. That's in the infrared region. So anything down to 2, it's in the visible spectrum. 3 down to 2 is red, 4 down to 2 is green, 5 down to 3 is blue, 6 down to 3 is violet. Anything down to 3 is infrared. Anything down to 1 is ultraviolet. Bohr predicted all of those spectral lines would be there, and they were eventually discovered. Okay? So as I've said here, if an excited electron emits energy and drops to n equals 2, so 3 down to 2, from a higher energy orbit, the wavelength of the emitted energy corresponds to a particular color of visible. 3 down to 2, that's red. 4 down to 2, that's blue. Or sorry, blue-green. 5 down to 2 is blue, 6 down to 2 is violet. This series of 4 bright lines in the visible spectrum is called the Balmer series. And if on the next page, I explain why that is. In 1885, a Swiss school teacher named Johann Balmer found an equation that was able to determine the wavelengths of the lines in the visible portion of hydrogen's emission spectrum. How did he do it? He just put a ruler on the bright line spectrum, and he measured the difference between where the lines go. And he came up with an equation that mathematically related those lines. He didn't know what he was doing. The electron was still 12 years away from being discovered. So he didn't know about electrons. He didn't know about atoms, none of that, subatomic particles. But because he was the first person to sort of mathematically relate where these mysterious lines were relative to each other, that series of bright lines, the visible spectrum, is called the Balmer series. Now we have 5 lines here. This is anything down to 2. So red, it shouldn't be, rather, this is just black, because that's blue-green. That's blue, that's violet, but violet from 6 down to 2 and 7 down to 2 look pretty much the same. So there's really only 4 lines. The first scientist to detect the ultraviolet spectral lines was a guy named Lyman. That's called the Lyman series. And the infrared, Passion, anything down to 4, anything down to 3, and bracket, anything down to 4. We can't see these because they're infrared. We can't see these because they're ultraviolet. Those we can see because they're in the visible spectrum. And if you want it done circularly, you can do it like that, but that's not the scale. And as the energy goes up, the energy differences get closer. Now, what we have here are, again, I'll turn the lights off for a second. So here's hydrogen bright line spectrum, and these things of wavelengths. Here's mercury. Now you might think, well, it makes sense that mercury has more lines because mercury has more electrons. Well, neon has far fewer electrons than mercury, yet there's far more bright lines. Every atom has a unique bright line spectrum, sometimes called a line print, like a fingerprint. What we have down here is hydrogen's absorption spectrum. In other words, if a hydrogen electron goes from 2 to 3, it's going to absorb red. So going from 2 to 3, it absorbs them. That's why we have that black line. Going from 2 to 4, it absorbs blue-green on the way up. Going from 2 to 5, 2 to 6. If you superimpose the emission spectrum on the absorption spectrum, you get a continuous spectrum. But the point is that only certain energies and not others are involved in this. And this is always what you see when you energize a gas. You see a bright line spectrum. Bohr's model of the hydrogen atom was successful in explaining the mystery of the bright line spectrum. Why the fact that the energy levels existed, and the fact that the energies were quantized was only occurred to him based on having seen Einstein give credence to Planck's quantum theory. The fact that it worked perfectly for hydrogen meant that Bohr was obviously on the right track. Bohr's model of the hydrogen atom was successful explaining the mystery of the bright line spectrum. His calculations worked for hydrogen and even calculated the radius of the orbit for hydrogens and electron in its ground state. In 1922, he was awarded the Nobel Prize in Physics. Now, I'm not going to ask you guys to do any arithmetic. I'm just sort of introducing this just to show you that it does work, okay? In 1888, another scientist named Johannes Rydberg derived an equation that could be used to calculate the wavelength of all hydrogen spectral lines. Now, neither Rydberg nor Balmer knew what they were working with. They didn't know where this light was coming from. They didn't know why it was discontinuous. The electron was still years away from being discovered. So there was no physical meaning to the variables that Rydberg, for example, put in his equation. But when you look at Bohr's equation, say for delta E, or the equation for wavelength of these spectral lines, and you superimpose it on Rydberg's, it's exactly the same. The only difference is that Bohr was giving physical meaning to what he was looking at. And the second video that we see, you'll see that. So it's not important that the actual arithmetic that Rydberg did, but the fact that there was a mathematical relationship is why this matters. This is worth mentioning because if a mathematical relationship exists for a natural phenomenon, even if we don't know what the phenomenon is about, it usually means there's a theory waiting to be discovered. Both Balmer's and Rydberg's equations were based on data, without any physical meaning to what they were calculating. Neither equation had any physical meaning in terms of atomic structure, but both worked. The physical meaning was supplied by Niels Bohr. He derived an equation for the energy associated with the electron in each allowed orbit, and therefore the difference in energy. He correctly predicted the visible, ultraviolet, and infrared spectral lines for hydrogen's emission spectrum by calculating the energy differences between those stationary states. Allowed orbit, same thing. Now, I said here that we're not going to do a rigorous mathematical treatment, and I expect you guys to do that. I'm just showing you that it works. So here's Bohr's equation for the difference in energy. When an electron is usually in a higher orbit, let's call that n sub h, say 4, the fourth energy level, drops to a lower orbit, let's say n equals 2, we're going to call that n sub l. That difference in energy is given by a constant times 1 over nl, the lower one, minus 1 over nh, the higher one. So for example, if the lower one's 2, 1/2 squared minus, if the higher one's 4, 1/4 squared. That multiplied by that gives the energy. Pretty simple. What about the wavelength? Well, again, I'm not going to expect you to derive this. Have you ever seen this equation before? For electromagnetic radiation? C is the speed of light. You guys know that's wavelength, right? What are the units of wavelength? Meters per wave. And what are the units of frequency? Waves per second, right? Or cycles per second. So if you multiply wavelength by frequency, you get velocity, meters per second. Okay. So electromagnetic radiation, the speed is the speed of light, right? Now you don't have to, I'm not going to ask you to calculate this, but that's true, which means that we can write this frequency as c over lambda, correct? So if we take this equation, and because frequency equals c over lambda, then we can put that, if delta E equals that, and that equals c over lambda, then we can replace delta E with FH times c over lambda, okay? And if we do that, and we divide both sides of this equation by this, we get this equation. Now, you don't have to do that, but I'm just showing you. Here we have something for calculating energy. Here we have something to calculate wavelength. So let's, for example, calculate the wavelength of the spectral line that would happen if an electron went from 4 down to 2. Okay? So we're going to calculate this. Calculate the wavelength in nanometers of the spectral line seen when hydrogen's electron falls from 4 down to 2. So we're going to use this equation. B is a constant, H is a constant, C is a constant. So that whole thing's a constant, and that is this. You guys seen that before? You know that that equals that. So something to the minus 1 is the same as 1 over the thing, right? Okay, so that's what that means. Let's use this calculation to calculate the wavelength. So we're calculating 1 over the wavelength. That's what's in the equation. So there's the constant. The lower one is 2, the higher one is 4. So there's the constant times that. And that gives us the inverse of the wavelength. So 1 over that gives us the wavelength. And nanometers, we multiply by 10 to the 9 nanometers per meter, and we get 486.0 nanometers. And if you look at this diagram, that's 4 down to 2. Okay, it works perfectly. Will I ask you to do that on a test? No, I won't. I'm just proving to you that it works perfectly, right? To which you would say, well, I thought 5.2 ended with a problem. Well, it does, we're just not there. Notice how these questions don't look the same as we did in stoichiometry. It's not calculated. It's just describe, explain, state, discuss. The only calculations are these 2 at the end, which I wouldn't give you on the test. Calculating delta E, calculating wavelength. Okay. Now, some students think, well, because there's not as much math, this is easier. Not necessarily. Some of you, and I've learned this through experience, that some of you who are really good with numbers aren't really good with explanations. And you almost have to know it better to explain it than you do to calculate it. So when I tell students, well, the majority of the arithmetic part of the course is done, people go, oh, I'm so glad. Careful what you wish for. So sometimes explanation questions are more difficult. Not only are there more of a pain in the ass to mark, but some students throw around terms that don't mean what they think they mean. Something as simple as one well-written sentence proves to be extremely challenging for more people than I thought it would. And knowing it well enough that you can put it into a clearly, stated phrase or sentence might mean studying it a little longer than you might have otherwise be used to. Niels Bohr firmly established the concept of fixed energy level. Although there were a few fine details of hydrogen's line spectrum that the theory couldn't account for, his model of the hydrogen atom appeared very promising. It worked perfectly for hydrogen. Now, what do I mean by this? Well, if you look really closely at those 4 bright lines, you can't see it in the book, but there's actually 2 lines of that color really close together. We call it the fine structure. Kind of like a little bit of a sort of a mini interference pattern. Bohr's theory couldn't account for that. But the fact that it was so good at predicting other things meant he was definitely on the right track. Unfortunately, when he used the same theory to predict the spectral lines of a multi-electron atom, even helium with 2 electrons, didn't work at all. And the more electrons an atom owned, the less well the theory seemed to work. All attempts to modify the theory to make it work were unsuccessful. So it soon became clear that the atomic puzzle hadn't yet been solved. Bohr assumed that an atom had only certain allowable energy levels in order to account for hydrogen's observed line spectrum. However, the assumption wasn't rooted in any physical theory. In other words, Bohr knew the energy levels had to be there, but not why they had to be there. He knew that if an electron was in one of these allowed orbits, it didn't radiate energy, but he didn't know why it didn't radiate energy. And that's not a comfortable situation for a physicist to be in. Because if you can't explain why, then it's kind of an ad hoc theory. Several challenges were leveled at Bohr, some insults. Some of the old guard in physics just quote referred to it as a cheap excuse for not knowing what was going on. So he knew this is how it had to be, but not why it had to be. It appeared that a new theory containing some bold ideas might be needed. So there's the problem. It didn't work for multi-electron atoms, and Bohr didn't know why the things had to be that way. Why the energy levels had to be there, why the energies of electrons and atoms were quantized, and why electrons in one of these allowed energy states didn't radiate energy. The new theory was eventually called quantum mechanics, and it had its beginnings in 1923 with the ideas of a young French aristocrat. You haven't heard this guy's name before. Louis de Broglie had originally earned a degree in history, but he was trying to decide on a subject for his doctoral thesis in physics. He had just learned that a professor in Missouri named Arthur Conklin had proven the existence of light quanta, later called photons, proposed by Einstein. A fascinating idea occurred to Broglie. That's all it was. It was just an idea. He didn't have any data to support it. It was just an idea. If waves behaved like particles, which had just been proven, could it also be possible for particles to behave like waves? In other words, why can't the reverse be true? By proposing that matter was wave-like, that particles had a wave nature. As it turned out, de Broglie was also suggesting a reason or why or theoretical foundation to the fixed energy levels of electrons and atoms. Now, how is that case? To understand that reason, we must briefly discuss some aspects of wave behavior. So let's say we have a string of length L fixed at both ends. It's under tension. It just means it's straight, like a guitar string. Those of you that are in physics, most of you ever heard the term standing wave? Standing wave, as the name might suggest, a wave that appears to stand still. So let's say we have a string of length L. And in that length, we have a string under tension. So double tight, like a guitar string. When we pluck this string, for a wave to not cancel itself out in this length, we have to, in that length, have a fixed number of half wave. So for example, that's a stable situation. You guys ever heard the term node? N-O-D-E? How many of you are in physics? You've never heard the term node? You're taking waves or have taken waves? Okay, a node is zero amplitude, right? Zero displacement, that's a node. So this is half a wavelength, right? A wave, a complete wave is that. Let's just take half of it. So this is lambda over 2. If I pick any point on the string, it appears to just stand still. It just oscillates up and down. That's why we call it a standing wave. It appears not to move. But it has to have a node at both ends to be stable. Now, the next stable situation is when I have two half waves. That's obviously one wavelength, but once again, I can maintain a standing wave. The next situation where I would have a node at both ends would be 3/2 wave, where to be like that. Okay? I have to have 3/2 wave. If I end with an antinode, in other words, if I start at a node at this end, and the wavelength is such that I end here, it cancels itself out. The wave destructively interferes with itself. So the condition for a standing stable wave in that length L is an integral number of half wavelengths. This stable or standing wave must have a wavelength lambda such that a whole number of half of them fit in the length L of the string. Any fractional amount of half wavelengths will cause the wave to break down by a process you guys have already heard, destructive interference. Thus, a stable wave can only exist if integral number of half wavelengths exist within the length L. That is, length equals 1 half wavelength, or 2, or 3, or 4, etc. N times lambda over 2 then, where n is a whole number, is the only stable situation. Any situation where n is not a whole number, like 3.3, will result in destructive interference. So what you could say here accurately is that this means that there is a quantum restriction, a whole number of those things on the maintenance of the wave. Unless 1, 2, 3, 4, or any integral number of half wavelengths exist in that room, the wave's going to break down. So there's a better diagram than I do. There's a guitar. Okay? Node at both ends. Now imagine bending this string around and closing it into a circle, representing an electron orbit. De Broglie considered what the requirements would be for a stable orbit if electrons did exhibit wave motion. He proposed that the only stable electron orbits were those whose size and therefore energy. Remember, the bigger an orbit gets, the more energy that electron in it has. Allowed for standing electron waves to be maintained. Orbits of any other size would cause the electron wave to break down, cancel itself out. So if we bend that string into a circle, here we have a stable situation. 3 wavelengths, 6 half wavelengths. That wave can maintain itself. And all it would appear be if the wave would simply oscillate. If the orbit gets bigger and we accommodate 5 wavelengths or 10 half wavelengths, that's also stable. But if we can't accommodate an integral number of half wavelengths in however big that orbit is, the orbit can't exist because the electrons will cancel themselves out. So, in the case of a guitar string, the condition for maintenance of a standing wave within a string of length L is a whole number of half wavelengths. A condition for maintenance of a stable electron orbit, a circular standing electron wave. That's why there are only allowed some energy states and not others. An important consequence then of prescribing a wave matrix to the electron is that it suggests a reason for the electron's quantized energy states proposed by Bohr. In other words, why? The only allowed orbits for electrons, and he labeled those orbits 1, 2, 3. The only reason they were those sizes and therefore those energies is because those were the only ones in which we could accommodate a standing electron wave. Now, Bohr didn't see the electrons. He saw it as a pure particle. But he couldn't answer why those energy levels were there, why those orbits were there. De Broglie said, you can't if you're treating the electron as a pure particle. But if you treat it as a wave, you can. That's a good test question. How does de Broglie's hypothesis suggest a reason for the allowed energy states of electrons proposed by Bohr? Simply put, the only allowed energy states or orbits for electrons and atoms are those whose size and therefore energy can accommodate a standing electron. That's the reason. You can't maintain that. The wave cancels itself out. Particles aren't supposed to do that, but waves can. In his PhD thesis, de Broglie derived an equation to actually calculate the wavelength of a particle. Math that had never been suggested before. And to do it, he put two famous equations together. Here's Einstein from 1905, and here's Planck from 1900. So if E equals that and that, then that means that that equals that. Okay? And if we remember this thing again, if the speed of light was the product of wavelengths times frequency, and that means that frequency equals c over lambda, correct? Well, let's replace that with exactly that. Now, de Broglie knew that no particle with mass can ever reach the speed of light. So he replaced speed, the speed of light, with just velocity. And notice we have two common terms here. Velocity here, velocity squared there. So if we cancel out, we end up with mass times velocity equals Planck's constant divided by wavelength. Or write it like this. That's de Broglie's hypothesis. You don't have to derive it. You just have to appreciate its significance. This is de Broglie's equation, and it's significant for several reasons. First, it tells us that any moving particle, whether it's an electron or a baseball, steady bus, felt tip, doesn't matter, has a wavelength we can calculate. Second, it shows that a particle's wavelength is inversely proportional to its mass. That's a constant. So as that goes up, that goes down. More importantly, as that goes down, that goes up. Third, and perhaps most important, remember the only thing I asked you to remember about Planck's constant was that it was damn tiny. That's all you need to remember. Third, and perhaps most important, because the value of Planck's constant is so very small, any particle big enough for us to see has a mass so big that the wavelength is incredibly small, ridiculously small. However, particles with a mass as small as an electron, and remember I put that in a quick check when I talked about Millikan's-Alldorf experiment. Here's the charge of the electron, here's the charge to mass ratio. What's the mass? 9.11 times 10 to the minus 31 kilograms. If we put that little tiny number down here, yeah, that's small. But if that's small enough, this isn't something we can ignore. And let's prove it. Calculate the de Broglie wavelength of two particles, one we're familiar with and one we're not. About a 100-mile-an-hour fastball. There's the number of major league pitchers can fill. 100 miles an hour corresponds to 44.4 meters per second. And a Major League Baseball has a mass of 140 grams, 0.120 kilograms. It is Planck's constant. So what's the wavelength of a 100-mile-an-hour fastball? 1.24 times 10 to the minus 34 meters. Let's put that into perspective. A hydrogen atom is 2.4 times 10 to the minus 10 meters. That's the diameter of a hydrogen atom. That's 10 to the minus 24, or 10 to the 24 times smaller than a hydrogen atom. That's more than Avogadro's number smaller than the smallest atom. Which means if you're going to pay attention to a wavelength that tiny to describe the behavior of a baseball, you're on crack. Imagine what a guy up to bat would do. He goes to bat and the pitcher throws a 100-mile fastball. He puts his bat down and goes, "Okay, folks, it's a wave." If he lives, he'll probably end up in the psych room. Does it have a wave nature? Yes, but it's ridiculously tiny. As the mass goes up, the wave goes down. Anything big enough for us to see has a wavelength that to concern ourselves with it would be ridiculous, if not dangerous. That makes sense because large objects that we can see, that our frame of reference, personal experience, and common sense tell us the particles behave precisely the way we expect them to, like particles. Gee, this is written well. Such objects don't pass through each other, create diffraction and interference patterns, and they certainly don't cancel themselves out. So to concern ourselves with a wave nature that is so insignificant would be ridiculous, if not dangerous. But the same isn't true for an electron. Let's do the same arithmetic for an electron. Look at how small the mass now is. The velocity of electrons is about 0.7% the speed of light. There's Planck's constant again. Now, yeah, 10 to the minus 34 is really tiny. And so is 10 to the minus 31. Now we get a wavelength 3.3 times 10 to the minus 10 meters. That's still small. It's 1.5 times bigger than the hydrogen atom itself. Imagine yourself thinking down and entering hydrogen's nucleus. Looking out from that nucleus at the electron, you might see a wave. So to a hydrogen atom, an electron is a wave. Does it have a particle nature? Sure, it's got a mass we can calculate. But it's got a wave nature that is so significant that if we choose to ignore it, then any attempt to correctly describe the behavior of the electron is doomed to failure. If the wave nature of electrons is so prominent, should we expect them to behave as other waves do? Should they produce diffraction patterns, be able to pass through each other, interfere with each other, and even cancel themselves out? As bizarre as it sounds, the answer is yes. That's why the electrons can't exist in any orbit other than the specified ones. Because if they do, the wave cancels itself out. The answer sounds bizarre because we have no experience with particles or waves on the scale of the atomic or subatomic. In that world where masses and distances are so small, neither particles nor waves behave the way we expect them to. In fact, the distinction between particles and waves doesn't even exist in that tiny enough. They're the same thing. In the macroscopic world of large objects, we have either particles or waves. Remember I said we live in a world of big solar things? In the world of the big, there's particles, there's waves. But in the quantum world, they're the same thing. Many in the scientific community, including Niels Bohr, were initially skeptical about particles also being waves. Then in 1927, Quentin Davidson and Lester Broomer, working at the Bell Labs in the United States, confirmed that electrons did indeed behave like waves. A beam of electrons was directed at a nickel crystal, and it generated a diffraction pattern, similar to that produced by electromagnetic waves such as X-rays. Only waves generate diffraction patterns. This proved de Broglie's hypothesis. So 2 years later, de Broglie got the Nobel Prize in 1929. The Swedish physicist who introduced him at the ceremony in Stockholm said, "When quite young, you threw yourself into the controversy, raging around the most profound problem in physics, the nature of matter. You had the boldest claims to it without the support of any known fact." In other words, just occurred to you, geez, when we behave like particles, how about the opposite? That matter not only had a corpuscular or particle nature, but also a wave nature. The experiment came later and established the correctness of the view. What important concept concerning atomic structure was Bohr's theory responsible? Well, the energies of electrons and atoms are quantized. Okay. He quantized the energies associated with electrons and atoms. Didn't know why, but he did that. And even our modern understanding of the atom still has that as postulate number one. The energies of electrons and atoms are quantized. That was Bohr's theory, but he didn't have a because. We now have a because of their wave nature. What does that mean? Well, the only allowed energy states for electrons and atoms are those in which we can maintain standing electron energy. Now, we'll get to that near the end of the chapter. We're going to summarize quantum mechanics in three postulates. Why did Bohr's atomic model need to be replaced? Well, because it couldn't predict behavior of electrons for multi-electron atoms. Now, ask yourself, why not? Why do you think Bohr's model didn't work for multi-electron atoms? Assuming the electron has a wave nature. What happens when waves are in the same vicinity of space? What do? What do waves do when they're in the same vicinity in space? Don't they interfere with each other? Particles don't. Waves do. And that's why a multi-electron atom, now there's interference. We got to take into account. Bohr saw the electron as a pure particle. He didn't even think of wave interference. But allowing electrons to have a wave nature makes perfect sense. It gets more complicated when they start to interfere with each other. If particles have a wave nature, why can't we detect the behavior in the big macroscopic world? Short answer, Planck's
Good
constant.
afternoon, Captain students.
Yeah.
Please prepare ourselves for grades before lunch.
Because that's
In the name of the Father, the Son, and the Holy Spirit.
macroscopic objects.
Bless us, O Lord, and these your gifts, which we are about to receive from your bounty, through Christ our Lord. Amen. St. Thomas More, Blessed Evan Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit.
You're not going to have to calculate the wavelength of a baseball or a carbine rifle bullet or antibiotics canister. That's just to give you the idea. What I'd like you to do, though, is read to the end of the section. You're going to read about Erwin Schrödinger. You're going to read about Werner Heisenberg. And then you're going to read about quantum mechanics, kind of melding those two ideas together. I'll try to finish 5.3 on Tuesday, and then we'll actually start applying this stuff for electrons and atoms. Right? Yeah.